Right. Okay. So yesterday we looked at all this horrible, SVT decomposition stuff and what we do with the metric. And at the end of the lecture, I presented a set of equations that allow you to relate the metric perturbations to the similarly SVT decomposed perturbations in the stress energy tensor. Okay. They are basically just based on the Einstein's equation. And they are kind of the equivalent of the Poisson equation. So in Newtonian physics, you have a Poisson equation that relates density, mass density to potential, and the equivalent of that is the Einstein's equation. And in our case, we have a set of equations that relate the perturbations. Now, so what I want to do today is to look more deeply at the perturbations in the stress energy tensor. In particular, what I want to do is to write down a set of equations to derive to show how these perturbations in T mu nu respond to perturbations in metric. Okay, and so just to set the scene, when we look at the lambda CDM model, then essentially there are only 4 forms of stuff that we track. Okay, so inflation happens and you have reheating, whatever, and you're left with radiation and matter. And essentially the 4 forms of stuff that we track are cold dark matter. There are 3 families of massless neutrinos in the standard lambda CDM model. There are obviously photons, because these are the CMB photons that we observe. And then there's also a lot of electrons and protons and helium-4 nuclei, and maybe, well, that's what we track. That's basically this bunch of stuff. And they're usually combined together and lumped together, called baryons in cosmology speak. Now, so these are the 4 things, and of course they are all responding to gravity, and therefore they have this interaction with the space-time metric. And in addition, the baryons themselves have, they have a Coulomb interaction keeping the negatively charged stuff and the positively charged stuff together, even if the electrons are not actually bound in the nuclei. And last but not least, you have the photons that can scatter off the electrons by Compton scattering. And that's also an important process. That's an important process in CMB physics, because that's basically what allows you to, photons to initially be opaque, so the universe will be initially opaque to photons, and then eventually when photon decoupling happens, so when photons stop scattering effectively off free electrons, because there are not enough of them around, then we see these photons at the CMB. Now, these collection of things seem kind of a bit, obviously they are motivated. They are, we know there are a lot of neutrinos around from left over from the Big Bang. We know there are photons. But if you think about it, think about these 4 kinds of things in terms of their interactions and kinematic properties, then essentially what they are simply the following. So, hang on, what happened? Okay, so neutrinos are essentially just relativistic, non-interacting stuff, whereas photons are relativistic, interacting stuff. If you go to the top quadrants, then CDM here, cold dark matter, are non-relativistic, non-interacting stuff, and the baryons here are non-relativistic, interacting stuff. So these 4 boxes essentially represent limiting behaviors, if you like. Okay. Now, we want to track how the perturbations evolve in these different kinds of stuff, and the way we do that, and how they interact under the influence of the space-time metric. And as you can probably imagine, the way we do it is to use the Boltzmann equation. Okay. So this here you've seen already. It's exactly the same slide that I showed last week. Anyway, you have the Boltzmann equation written in this covariant form, and F1 here is the one particle phase space density that we need to track. And on the left-hand side in general, that's the Liouville operator, and on the right-hand side you have the collision term. Okay, so this is in covariant form, the collision is Lorentz invariant, the whole thing. And so that's the general form. The phase space density is defined such that you can write down a phase space volume, like so. And if you multiply the phase space volume by the phase space density, you end up getting the number of particle 1 that you have in that phase space volume. Just to remind you what the collision integral looks like, it's this horribly ugly thing that you have to integrate over for this is a 2-to-2 scattering process. You integrate over this horrible 9-dimensional phase space. You have the matrix element and then quantum statistical factors. So you've seen this before. What is new, however, at this point, another equation I'll introduce is this one. Once you have figured out the one particle phase space density, then you can immediately use it to construct the stress energy tensor. And here it's written in this covariant form. Again, I'm just giving it to you as a fact. You can justify the form of this thing and also kind of derive it more rigorously, of course. I think probably I've seen that done maybe in Ruth Durer's textbook. Not many people really show you how it's done. But anyway, this is an expression that we will come back to because we need T mu nu in the end. Okay. Now, okay, so that's where we start. Okay, so these are all general, okay? You can apply these equations to whatever setting you want. You can do early universe physics. You can do stellar physics. These are just general. However, since we're trying to use this framework to do perturbative cosmology, then there are certain ways to rewrite this equation, this set of equations that make it just a little bit easier to understand what is happening. Okay, so one thing we can do is to, instead of using the form momentum as a momentum variable, but actually choose a frame and then consider what is the momentum that is observed by an observer in that frame. And in cosmology, the special observer is the co-moving observer. Okay, the observer who is at rest with the coordinates of your coordinate system. Okay, that's the co-moving observer. That observer is always special. So, rather than using the form momentum as a variable, we just simply ask, let's just re-express my one particle phase space density in terms of the physical momentum measured by that guy. Okay, so that's the first thing we do. So instead of writing f x alpha pi, we just go to f x alpha and then a physical momentum. So this is the physical momentum measured by a co-moving observer. Okay. There's one more thing we can do to make it even more amenable to cosmological treatment. And that is, if you remember from last week, one thing about physical momentum in an FLRW universe is that it redshifts. Okay, it goes away with, it drops off with time, like a to the minus 1, like the scale factor raised to the minus 1. Okay, so that's like a given thing that just happens in an expanding universe. So in an inhomogeneous universe, well, that is only a little bit inhomogeneous, you're still largely, the momentum, the evolution of the momentum is still largely governed by this redshifting. Okay, there'll be some deviations, but this, going like a to the minus 1 behavior will also be largely present in how the momentum evolves. So another thing we can do is to just define another parameter, which I'll call Q. And you've seen this Q before from last week. And Q is simply defined as the scale factor times the magnitude or the physical momentum. And the role of defining this Q is simply that I scale away most of the expansion, the redshifting behavior of the momentum. Okay? Now, it's important to remember that this thing here is not constant in time. in an inhomogeneous universe. Okay? We just define it just to get rid of the main behavior, but it actually changes with time as a result of the inhomogeneities. Okay, so we have Q. You can also define an equivalent quantity, which is kind of like a rescaled energy. And this is just defined as A times the energy of whatever particle species you want to look at. And this is equivalently written as Q squared, so the same Q as above, plus A squared, M squared, where M is your particle mass. Okay, so that's good, now that we've defined these things. So we've defined these things, then it also means that instead of using P as my independent parameter, I can also just further replace P with Q. Okay? In fact, I should write down here. No, actually, let's do it down here, it's easier. So F P now goes to F. Okay, so I have here X alpha as just the 4 coordinates, so I have time and the spatial coordinates. Okay, eta is time, conformal time. Xi are the co-moving coordinates, and I just define Q, which is the magnitude, this kind of rescale magnitude, the magnitude of this rescale momentum. So that's Q, and then I write down also the momentum direction as well, which I'll call Ni. Okay, so okay, that's good. Now that we've decided what the independent variables should be, then I can immediately proceed to rewrite my Liouville operator and my Boltzmann equation in general in the following way. So I'll still have the time part, of course, it's always there. And since now, and I have the spatial coordinates, this would be dxi, d eta, d partial f, partial xi. And now I have dq, d eta for this momentum variable, and then df, dq. And then I have the rate of change of the momentum direction, and then df, dni, and then last but not least, I need to tag on the collision integral on the right-hand side. And so I'll still have the CF, but now because I start with df, d eta, if I compare that with my original expression, it's clear immediately that this thing here has to be divided by the 4 momentum, a 0th component. Okay? Which you can evaluate given your metric to see how this P naught relate to these parameters as well as the metric, but that's dependent on which gauge you choose, etc. So I'm not going to bother doing that, at least not at this step. Okay, so that's my Boltzmann equation, rewritten in a form that is a bit better for cosmological calculations. Now, the next thing we need to do is, well, first of all, we realize that we want to do perturbation theory anyway. And so what we can immediately do is to split up the one particle phase space density into a homogeneous and isotropic part and a perturbation. So if you think about photons, for example, the homogeneous and isotropic part would just be the Planck distribution. Okay, because you have photons that are, if you don't put in perturbations, they should just have a Planck spectrum. Okay, so you split F, eta, xi, q, ni, into F bar, which can be a function of time and a function of this Q parameter, this momentum parameter, but it cannot depend on the spatial part, the spatial coordinates, can't depend on the direction of the momentum either, obviously, otherwise you violate homogeneity and anisotropy. And then you have the perturbation part, which can depend on time, space, momentum direction. Okay? So as said, this thing here, which would be, for example, for photons, that would be basically the Planck spectrum. If you're dealing with neutrinos, then this would be the relativistic Fermi-Dirac distribution. Okay. Now, then the rest is really just about plugging this kind of split up form of the phase-space density back to the back to the Boltzmann equation, and then just keeping terms to the correct order. All right? So if I look at the zeroth order case, then I'll be looking at the time evolution of F bar. Okay. Now, if I go to the second term, F bar has no dependence on the spatial coordinates, so there will be no second term for the zeroth order Boltzmann equation. Similarly, here we have a df dq. Now, obviously, F bar here depends on Q, so my df bar dq will be non-zero. However, I also have this dq d eta, okay, which is essentially how momentum changes with time. Now, I highlighted before that if you are in an inhomogeneous universe, Q is not a constant of time. Okay? However, if I'm doing perturbation theory and I'm only interested at this stage at what happens at zeroth order, then Q in a homogeneous and isotropic universe is a constant of time. Okay? So again, this means that I don't have this term either in the zeroth order case. And last but not least, I have df dni, so any kind of derivative of the phase-space density with respect to the momentum direction. And again, for the zeroth order case, my F bar does not depend on the momentum direction, okay? Because then otherwise it would violate isotropy. So what this means in the end is that my zeroth order term is really just df bar, d time, and then what I'm left with on the left-hand side would be 1 on p, 0, and then the collision term. Again, all of this expanded to zeroth order. Okay, so this zero here doesn't mean scalar, zeroth order in this case. Okay, now P naught is still something I didn't evaluate, but you probably figure that one out anyway. If I'm in a homogeneous and isotropic universe, then P naught is essentially just pretty simple energy, maybe with a few scaling of the scale factor. And in fact, it looks like this. It's actually just a square epsilon c f at zeroth order. And if I relate it back to just the energy rather than my funny epsilon, then this is just zeroth order f. And this is familiar to you. That's exactly the Boltzmann equation that you use in tracking dark matter production, for example. Okay? Now, of course, that's the zeroth order thing is not interesting for our purpose here. Well, I mean, it's not uninteresting. It's not the most relevant. The more relevant case is that of what happens if you go to first order. Okay, so here what we want is df, d eta. And f here is the perturbation, so I would which depends on both the momentum as well as the spatial coordinates. So in general, I would expect this second term to be present. So I will have, hang on, just let me have a look at something. Oh yeah, okay. I would in general have dxi, d eta, and then df, dxi, and then I will also have the third term, because now the third term here I have a dq d eta, so any kind of change of the momentum parameter as a function of time, and which is non-zero if you're looking at perturbations. And now I have to multiply this by df bar dq, okay? Because if I have some first order effect that changes the momentum with respect to time, so actually put a 1 here to indicate first order, then the only way to make this all consistent and first order is to make sure that I multiply by a zeroth order term here. So that's why this is df bar dq. And that's it, because this last term here will automatically be higher order, okay? Because I have no df bar dni to begin with, so this would always be at least first order, and any change in direction of the momentum will also be first order. So this term this term over here will be, will only come in as second order. So at first order, it disappears. Okay, so that's good. So I have all of the left-hand side, and last but not least, I tag on the right-hand side a collision term, which I'll write like this, and then put a 1 there to indicate this first order. Now, this is not in the nicest looking form yet, but we're not far away from the nicest looking form. We just have to do one more thing, and that is when I see dxi d eta over here, this is essentially just the corner velocity of a particle, okay? So in other words, it will be the direction of the velocity would be the same as the direction of the momentum, ni. And to establish the velocity, the corner velocity, you can just do something as simple as taking the momentum and divide it by the energy, as usual. So in other words, all of this over here, I can actually just rewrite as q divided by epsilon, and then ni. Okay, so let me actually just replace that whole term so that I have the full expression there in a nice way. So I get rid of that. And I replace it with q epsilon ni. Okay, good. Good, that's my first order Boltzmann equation, including collision term. Now, so this is what we solve for. This is just the momentum divided by this rescale energy. Ni is the direction of the momentum. This tells me how the phase space density changes with spatial coordinates. And then I have a df bar dq, which is basically just a momentum derivative of the background. Now, one thing I need to specify still, and that is dq d eta. Okay? Now, this is funny notation, but physically, what dq d eta is really just the rate of change of momentum with respect to time. Okay? And in classical physics, you know the rate of change of momentum with respect to time is equal to force. Okay. So we know immediately that dq d eta has to be something related to the metric perturbations. And so that's essentially where the influence of the metric perturbations come in. It's through this term. Okay? And to figure out what dq d eta is, and I'm not actually going to do it, I'll just give you the expression. All you have to do is to appeal to the geodesic equation. Okay? So, which normally looks like this. Okay, textbook stuff. And all you have to do is basically map your, all of these four momenta here to the momentum variable that we actually want to use. And it's just, after several lines of work, what you arrive at for dq d eta at first order will be something that looks like this. So you'll have a minus epsilon ni di phi. Oh, sorry, not phi. Psi plus q phi dot minus q ni nj hij dot v plus hij dot t. Okay? Assuming that we express our metric in this way. So that's just a general way of writing my metric. Psi is this one of these Newtonian gauge perturbations. And Hij here is just the other Newtonian gauge perturbation, gamma ij. And then the rest of it could be kind of Hij coming from vector contributions and Hij coming from tensor distribution, which I didn't bother writing out exactly, but this is kind of a shorthand notation. Okay, so this is essentially the rate of change of, I said that's the rate of change on the momentum with respect to time, and all of this stuff here on the right hand side is basically the forces acting on the system. Okay, now, then having figured out these things, then the next thing that we have to do is simply to, in principle, stick these things into the computer, solve them, and then you have the perturbations solved for F, and then once you have the solution for F, you can stick them back into the stress energy tensor, which is written up there. And if I do a little bit of work to massage them into the right form, then what I'll find is basically a list of expressions that allows us to relate the perturbations F to the energy density. So this is just a simple integral of energy, this energy parameter, epsilon, times the phase space perturbation. That gives you the energy density perturbation. The energy flux would come from essentially just the momentum direction, multiplied by the perturbation. That gives you the energy flux. And similarly, the pressure over here, you have this 1/3 Q squared divided by epsilon. And F, again, is the perturbation in your one particle phase space, and then also the anisotropic stress. Okay, so these are essentially just derived from the T mu nu expression from the previous slide. Now, so at this stage, you might ask me, well, we wasted all this time doing SVT decomposition yesterday. And then now you look at this Boltzmann equation that I just wrote up, and this phase space density. That looks like a scalar, right? So what happened to all of my SVT stuff? You know, everything looks like just a nice scalar integral. Well, actually, not completely. That is not completely true. That is because if you examine the form of the Boltzmann equation, okay, so you have the force term coming in here. Okay, that's the rate of change of the momentum with respect to time. And over here, you see that there are different, you know, tensorial structures in this equation. So you have some nice. So here you have, you know, basically this Nij, which is basically totally tensorial. Okay. So what it means is that you can actually apply another decomposition to the phase space density itself, and also to the phase space density perturbation itself, and also to the entire perturbed Boltzmann equation. Okay, and decompose that according to what the structure of this force term over here. Okay, and once you do that, you will actually completely recover the SVT components again. Okay, so you'll end up having, once you do the decomposition, which I'll show you in a bit, you'll end up having again separate equations for those parts of the phase space density that evolves like scalar, and those parts that evolve like vector, and those parts that evolve like tensors. Okay, and a trick to the decomposition is to make use of spherical harmonics. Okay, let's see what I can clean. Maybe that one. Okay, so what you do is that you write your perturbed part of the one particle phase space density, which is generally a function of time, xi, q, and I. And then what you do is that you, as said, you decompose. Okay? And here you have basically something that looks awfully like spherical harmonics at this stage, and in the end you'll see that they're just spherical harmonics. And then L equals 0, infinity. And then there's usually a bunch of prefactors depending on convention, which I won't bother talking about. And then you have these coefficients, which are dependent on L, multiple L, and then the m's which go from minus L to L. And the independent variables of this coefficient here is eta, k, and q. And then you have a bunch of basis functions, gm, ki, xi, and I. Okay, where glm, ki, xi, and I is equal to basically all your momentum directions, 1, and I m, and then q, m, I1, I1, m, sorry, like, no, what's it called? Like so. Okay, so these are the same eigenfunctions of a Laplacian that we talked about yesterday. Now, if this is a bit cryptic to you, essentially what we're doing is that you pick a wave vector direction, k, and then you ask about how the perturbations behave according to which way the momentum vector points. Okay, how does it align with the vector k? Okay, is it completely aligned, a little bit offline, transverse? Okay, that's what this decomposition is about. Now, as I mentioned earlier, this is essentially just a spherical harmonic decomposition, and okay, in general, it's not true if you are in a non-flat space. But if you're in a flat space, this is essentially just spherical harmonics plus a plane wave. Okay, so these basis functions AI, Xi, and I are just spherical harmonics M, L, and I multiplied by a plane wave. Okay, so just to remind everyone, K here is the wave number, a wave vector, sorry, of the perturbation. And Ni here, it's the momentum direction. And so that's what we do. We take the perturbed part of phase space density, and then we just subject it to a plane wave as well as a spherical harmonic decomposition. Now, if you've forgotten your spherical harmonics, that's what they look like. And so essentially, we are just looking at, if you imagine that your k vector points in the y direction, then you're just looking at basically the perturbations in, so the zeroth mode will be basically those longitudinal perturbations that are aligned with the k vector, and then you, and any of the m equals -1 or m equals +1 perturbations will be transverse to the k vector, which points in the z direction, sorry. And then you could also have these m ±2 perturbations that are again transverse to the wave vector, but kind of transverse in a different way compared with the m ± modes. Okay, so the connection of this back to the SVT decomposition is immediately clear. 0 is scalar, ±1 are the vectors, and ±2 are again just the tensor modes. Okay, so that's basically how we recover this SVT language. We go back to this SVT language, even though at least at first glance, when you look at the Boltzmann equation, it looks like we have completely lost it. Okay, but you recover it once you do the spherical harmonics decomposition. So that's good, because now if we were to apply this decomposition to the, let's see, which one can I clean? To I, yeah, okay, so I don't have to clean anything. If I'm to apply this decomposition to the whole Boltzmann equation, okay, so do all of that to this whole equation, what I'll find immediately is that the decomposition will single out the first two terms for m equals 0. Okay? And it will single out this term for m equals ±1. It will single out this term for the dq d eta for m ±2. Okay? So that's what's going to happen once you do that calculation. And the important thing here is that the different m modes don't mix. Okay, we're only interested in doing things to linear order. So again, you have the separation of scalar, vectors, and tensors from each other, which is what is desired. Okay, now then you may ask, okay, that's cool, you separate out the SVT, but is there any other advantage to doing this decomposition? And the answer is yes, definitely. And that is because it actually makes the physics of the Boltzmann equation much clearer than what you're seeing over there. So to begin with, let's go back to these expressions for the density, pressure, velocity, stress, etc. So previously, I just wrote them up as they were meant to be. So you just have these integrals, okay, of the phase-space perturbation, and then you construct the energy density, energy flux, pressure, and isotropic stress in this manner. But once you do this horrible decomposition, what you find immediately is that the energy density is actually related to the monopole, and it is only present for scalar modes, which is what we should expect as well, because density perturbations is a totally scalar thing. Okay. You can go down to energy flux, and then then figure out what goes towards this. And what you find is that to construct the energy flux, you only need the dipole of the perturbations. So L equals 1. And since L equals 1 has 3 m's, you have 0 and plus or minus 1. And then you've got to sum over them as well. But that's exactly what we expect, right? Because here, if you go back to the left-hand side of the slide, you see here there's a velocity, right? And the velocity, we know, has a scalar component and a vector component. So what you find here essentially is that when I construct the energy flux from my phase space density perturbations, then I just need to take the dipole and then all of the 3 components that we have, put them all together, and then I have it. I have my entire velocity perturbation. Pressure, now this is cool. Pressure is a scalar again, and also it's dependent on L equals 0, the monopole. Okay, so the same monopole that goes into energy density goes also into pressure. So they are not, I mean, these two things are related, basically. This is what it's telling us. And last but not least, the anisotropic stress here is the fun one, because now you have actually a dependence on the quadrupole. Okay, and quadrupole has 5 components, so you've got to sum them all up. So essentially, these are the one scalar anisotropic stress, and the 2 components of vector anisotropic stress, and the 2 components of tensor anisotropic stress that goes into this last part. You can, of course, keep going to L equals 3, L equals 4, but I don't think they have names. And they don't go into any higher multiples, don't go into the stress energy tensor anyway. So that's where we stop here. Now, that's one advantage, because you can clearly identify the meanings of the physical meaning of the different multiples, okay, and how they map back to things like energy density and energy fluxes, etc. There is one. Well, actually, that's the advantage. Okay. Now, so here's the Boltzmann equation again, which is essentially just the same as what I have written on the board. So the first one here is up there, the first equation, and then the dq d eta is the same as this equation over here. So as already mentioned before, all the different m modes would decouple. But there's one peculiar feature in here, which is actually ends up being quite important, and that is the second term here. You have the q epsilon, and then you have ni, and then a derivative of the perturbation. This term is actually quite fun, and that's because once you do the spherical harmonics decomposition, what this term does, okay, what the derivative does here, is that it ends up linking all the equations for the multiple Fl to the multiple below and the multiple above. Okay? And in fact, if you were to do the entire decomposition for all possible values of L, what you'll find is what we call a Boltzmann hierarchy. Okay? So you go from a Boltzmann equation like that, you apply the decomposition, and at least in the scalar case, this is what you end up with. This is what you will end up with. You have an equation for the monopole, which again has the structure of having a source term and a collision term, and then you have the monopole equation, source term, collision term, and then so on and so forth. You have L equals 2, which is comes with this more general, as a general form for this expression, and and you keep going all the way to infinity. Okay, so so the feature that I mentioned in the previous slide about coupling, you can see here. So you examine in particular this equation, for example. This is the equation of motion for the dipole, and you see that it depends on the monopole, which is the multiple below, and then it also depends on the the quadrupole, which is the multiple above. Okay, and you see this linking structure here as well. So equation of motion for L, but it's linked to L minus 1 and L plus 1. Okay, so this means that this hierarchy, this thing called Boltzmann hierarchy, just keeps going to infinity. And that's basically, you get to that, and essentially because when you do the decomposition, the multiple decomposition, essentially what you're doing is you're looking, the L parameter there is basically talking about, it's basically corresponding to the alignment of the wave vector and the momentum vector. And there are infinitely many different angles that alignment can take on. And you basically just reparameterize that angle into an infinite number of degrees of freedom, okay, in the form of the L multiple parameter. Okay, so that's a Boltzmann hierarchy. This is the hierarchy for the scalar case. You can, of course, also do one for vectors, but no one cares about vectors much, so I don't show that. You can also do one for the tensor modes, which actually has a particularly simple form. But again, you see this coupling between the L minus, coupling of the L mode to the L minus 1 and the L plus 1 multiple. You have a gravitational source term over here, and again, you have a collision term. And again, this is a hierarchy that is infinite. Okay, and in this case, the hierarchy starts as L equals 2, okay, because you have no L equals 0 or L equals 1 tensor modes, and it extends all the way to infinity. Okay, yep, so that's the Boltzmann hierarchy, which I'll show you again. Okay, that's the scalar one, which we will use more often than we do the play with the tensor one. That's basically all you need if you want to describe perturbations in stuff like dark matter, neutrinos, photons, whatever. This is it. That's the basis. Okay? And we've taken about 45 minutes to get to here, which is actually not bad. Okay, so does anyone want to ask anything at this stage before I move on? I'll take that as a no. So then I'll move on. Okay, so as said, that's the master equation, if you like. Now, in practice, however, this master equation is rather nasty because you have this infinite hierarchy. Okay, so if you want to stick it in your computer, you have to solve an infinite hierarchy. Okay, in practice, of course, you truncate it somewhere based on some criterion or criteria. But nonetheless, it's infinite. Then you also have to, there's also one such hierarchy for each momentum mode that you want to consider, which can also be an overkill for certain purposes. So what I'm going to do now in the next 45 minutes is to take this thing and then reduce it to something that can be used for different types of stuff in the universe. Okay? So here we go. Now, as said before, there are 4 types of things that we normally track when we do when we look at cosmological perturbations. So the simplest thing here that we so there are 4 of them. Okay, you have corresponding to different limiting behaviors. Okay. So let's look first of all at cold dark matter, because that's by far the simplest. So, if you had cold dark matter, and so let's actually just have this for reference then. You have cold dark matter. Remember, the definition of cold dark matter is that it's something that doesn't have any pressure. At least that's what we do at the homogeneous level. You see, when I want to describe matter, you just say P is equal to 0. That's it. Now, the equivalent statement I can make with respect to this picture is that whenever I see terms, so this is non-relativistic, okay? And normally you say P bar is equal to 0. Okay? And at first order, what we can say equivalently is that every time I see terms that are proportional to Q divided by epsilon, so Q divided by epsilon is basically speed, and raised to the power n, where n is equal to or larger than 2, then I drop it. So that makes life a lot easier. Because first of all, it means that I don't have to worry about pressure. I don't have to worry about anisotropic stress either, because anisotropic stress is, pressure is isotropic stress. Okay? So pressure has an inherent dependence on the velocity square. Okay? So I drop pressure, I drop anisotropic stress. So immediately, the only things that I need to worry about are the energy density perturbations. Which are like delta rho is equal to a to the minus 3. Actually, let's have that in front of us so that we know what we're looking at. So we're looking at the first term, first expression up there. And then I will also, okay, so I have a 4 there to begin with, right? But I have D3Q, I have the energy in there, which in this case would be A times the mass of whatever dark matter particle I'm dealing with. And then I will also have the monopole fluctuation. Okay? So rewriting this, simplifying it a little bit, I have the scale factor in here, which cancels out with one scale factor out the front, so I have a to the minus 3 left. And the mass is constant, so I factor it out as well. And then I have a nice D3Q F naught in here. Now, the other term that is also not high order in the velocity is the energy flux, because that only has one count of the velocity in the expression. So this can be written as P bar VI. I drop the pressure, okay, because that's small for cold dark matter. And again, I have a to the minus 4, and then a to the minus 4, and then D3Q, M, and then, so hang on, that would be, sorry, AM, like that. And then I have the Q over here, the epsilon becomes AM, and then NI, and then again I have all my scalar and vector dipole components. Okay, so that's energy density perturbations that, and the energy flux that I have for cold dark matter, and everything else I don't need to worry about. So that's good, because now this tells me immediately that I don't really need to worry about what's happening with the higher order multiples. Actually, this alone doesn't really completely tell you that, because, hang on, well, okay, it sort of does. We only need to compute the monopole and the dipole in order to figure out what dark matter is doing. Now, that's the stress energy tensor itself, but still I have the Boltzmann equation. So what I can do is to do the same thing, okay? I can apply these integrals, okay, I can apply the first integral to the first monopole equation up there, okay? And if I did that, okay, so I do, so I integrate the L equals 0 equation over momentum. What I would get is, well, without doing it, what I'll get is essentially an equation for delta cold dark matter, which is defined as delta rho divided by rho. Okay, so I put a C there to indicate it's cold dark matter. And that equation would look like this. Delta C dot, okay, that's from the left-hand side. And then on the right-hand side, Integrating over the dipole term would give me a k over there. And then for the scalar component, since I'm just indicating a scalar hierarchy over here, this would be the scalar velocity. And then last but not least, I also have the gravitational source term that's proportional phi dot. And once I do the momentum integral, what I will find is that this corresponds to plus 3 phi dot. Okay? Dark matter is collisionless, so there's no collision term, but that's what you end up with if you just apply the momentum integration to the first equation up there. You can also integrate the L equals 1 equation over momentum. And when you do that, you will end up with an equation of motion for the velocity itself. And well, at least for the scalar part of the velocity. And again, this is an integral that you can do quite easily. And what you end up with once you do that is an equation for V naught, okay? And there will be no dependence on the quadruple, because the quadruple itself is higher order in velocity. It's one of those terms where Q divided by epsilon has a power more than 2, okay, so we can drop that. Similarly, the F0 term will also drop out, because when you do the integration, you have basically another factor of Q on epsilon coming in, so it turns out that this term over here also has too many factors of Q divided by epsilon. Okay, so you can also drop this term. So the only thing that's left once you integrate the L equals 1 equation is just the gravitational source term. However, there's actually also a damping term that arises because of the way the integral is constructed. There are some factors of a to the minus 4 that are in there, and this integral here is for rho bar times VI, whereas we're interested in VI. Okay, so there's some residual factors of A in there, which actually ends up leading to a kind of damping term in the final equation of motion. So actually, the equation that you end up getting is something like this: curly H, V naught, and then minus K psi is equal to 0. Okay. Now that's what you get if you look at scalars. And of course, you can also do the same thing if you are interested to figure out what the vector equation of motion is. And when you do that, then what you'll find is another equation of motion for V plus or minus 1 dot. And this one only has a damping term. If you're in an inflationary universe, you have no source term, so that's just the only thing that's left. Okay, so these are the 3 equations that I can derive from the Boltzmann hierarchy under the assumption that the velocity dispersion of the stuff I'm dealing with is small. So I drop all the terms that are higher order in velocity. Okay, so that's how we describe cold dark matter. Okay, so what we've done is to essentially reduce the equations from a rather horribly complicated Boltzmann hierarchy into 3 fairly simple equations. Okay, so that's cold dark matter. Now, this is only true for cold dark matter. Okay, I'll say a couple more words about warm dark matter in a bit. Okay, so that's one limit for non-interacting and completely cold and non-relativistic stuff. Just 3 equations and that's it, done. Okay, now, then the next thing we can look at, which is also a nice limiting case, is that of relativistic neutrinos, okay, massless neutrinos, which is this case over here. The thing about massless neutrinos is that well, again, they are not interacting, so I can immediately set all collision terms to 0, which is good. Okay. Now, if we go back to the Boltzmann equation, which I unfortunately just rubbed out, but anyway, it doesn't matter. If you go back to the Boltzmann equation, but I have it on slides, so I'll just show you that. If you go back to the Boltzmann equation, before we did all the decomposition, what you see immediately is that for totally ultra-relativistic species where Q, momentum, is equal to the energy, then you're left with an equation which is just dF d eta plus Ni dIf, and then you have, I'll rewrite this as d log Q d eta, and then dF bar d log Q. Okay? And if I also examine the rate of change of the momentum in this limit, what you find is that d log Q d eta is equal to minus Ni di psi plus phi dot minus Ni Nj Hij V plus Hij T. Okay? So that's nice. Why is it nice? Because apart from the fact that you have this dF bar d log Q factor, the rest of the system is actually completely independent of the momentum. Okay? This is the only momentum dependence in the entire equation. Everything else is, well, you know, that's d log Q d log n eta is not momentum dependent whatsoever. So what this means is that instead of having to track the perturbed phase space density at every single momentum mode imaginable, you can actually make your life a lot simpler and then just track one variable. And having tracked the once you track the variable, you can simply relate it back to perturbations in the momentum mode simply by rescaling it by dF bar d log Q. And in fact, the variable that we usually use is called, it's essentially like a temperature variation, perturbation, and it's defined as follows. It's basically F eta xi q ni, and then you have the minus F bar d log Q, and then delta eta xi ni. Okay, so that's a definition. So dF bar d log Q is exactly the same as that appearing above, and this delta here is essentially a temperature fluctuation for the neutrinos. So the advantage of doing this, as said, is that the momentum dependence is entirely here in this prefactor, and the rest of this function here, the temperature fluctuation, depends only on time, space, and the direction of the momentum. Okay, and one further advantage is that you don't have to, if you use this variable instead, then you don't have to solve the Boltzmann equation for every momentum mode, okay, which is a huge advantage. Okay, so in fact, if I am to rewrite the Boltzmann equation in terms of this delta parameter, and then what I would find is following. So instead of df d eta, I'll have d delta d eta, and then ni di delta minus d log minus d log q d eta is 0 to 0. Okay. So that's the first order Boltzmann equation for massless neutrinos. And as with before, when we did the spherical harmonics decomposition for the capital F, you can also do exactly the same spherical harmonics decomposition also for the temperature fluctuation delta. Okay? And once you do that, what you could expect to get again is a huge hierarchy, a Boltzmann hierarchy. Okay? Now, so that's the Boltzmann hierarchy for massless neutrinos after basically applying, basically after we decompose this equation here for the temperature fluctuation. There's one more thing that I didn't say, and that is delta nu here is essentially delta rho nu and divided by rho bar nu, and this is equal to 4 times the temperature fluctuation monopole. And V here, neutrino, is the velocity perturbation, scalar velocity perturbation, and this is 3 times the dipole, and so on and so forth. Okay? And so as said, it's another Boltzmann hierarchy that you get, but now we don't have to worry about individual momentum modes because they all evolve in essentially the same way. Now, okay, so immediately you see that there's a huge difference between the equation of motion for neutrinos and cold dark matter, simply because in the cold dark matter case, these things are cold and non-relativistic. For massless neutrinos, you basically always have this population that is ultra-relativistic. You have, well, if you compare the two sets of equations, you have, well, there's some small structural differences as well. So for example, you have, delta nu, the source, gravitational source term here is 4 times phi dot as opposed to 3 times phi dot. And, but for the velocity part, you have, well, psi over here, again, psi over there, so that's nice. The higher order multiple moments were completely missing in the case of cold dark matter because we explicitly dropped them, but in the case of neutrinos, you cannot. Okay? And again, as said, this is a Boltzmann hierarchy, so it goes to infinity. Now, another thing that, so what does the presence of these high multiples do? Well, this is actually cool, and see, if you look at this Boltzmann hierarchy here for the massless neutrinos, as said earlier, what the hierarchy does is that it couples a mode L to a multiple below and a multiple above. So what this means is that if you look at, for example, the dipole equation, the monopole acts as a source for the dipole, okay? But the quadrupole here is sucking away power, so it's a sink. Okay, so in other words, what you have is that you could have external sources that might be kicking up power for the monopole, but then this power would be leaked to the dipole. Okay, and then through this coupling, and then the dipole power will be leaked to the quadrupole through this coupling again, and once you get to the quadrupole, it will be leaked to the L equals 3, and so on and so forth. Okay, so what you have is basically a transfer of power from the low multiples to the high multiples in a manner that looks like this. Okay, so you get your gravitational source terms at L equals 0 and 1. And then this power gets passed on to the higher multiples. And this is essentially the effect of free streaming in inhomogeneities. Okay? This is what free streaming does, and neutrinos free stream. Okay? Dark matter doesn't. Okay, so you have free streaming allows you to transfer power away from the low multiples. And the importance of that is that the low multiples are things like the L equals 0 multiple is density perturbations. Dipole is velocity perturbations. And if you keep sucking out power from the monopole and the dipole, then effectively you have none of the monopole and the dipole left. And that is basically the phenomenon, essentially the phenomenon that we talk about free streaming things and then wiping out perturbations. Because the structure of the hierarchy just allows you to basically transfer all the power to the higher multiples and then to infinity, and you have no power anymore in the low multiples. Okay, so that's free streaming, okay, which is illustrated here in this plot. So you have the quadrupole here in the red, so it gets kicked up, and then very quickly it drops down because this power is transferred to green over here, which is actually L equals 5. And then you have L equals 10 peaking, L equals 15, and then they all eventually die away as a result of this free streaming effect. Now, of course, real neutrinos are massive, okay? So the case I told you here is not really real neutrinos. Real neutrinos are massive things, okay? So what it means is that what I just showed you, that treatment there with using this temperature fluctuation as a proxy is actually not a good idea at all, because for sub-electron volt neutrinos, which are the standard model neutrinos, what we expect standard model neutrinos to be, they actually started out life as totally relativistic particle species. Okay? They only transition to a non-relativistic species at a pretty late time, at a redshift of maybe 100 to 1,000. And we expect them to be non-relativistic today technically, but they are not completely cold. In fact, they are kind of, well, hot, okay? And furthermore, they spend a substantial amount of their lifetime as relativistic particle species, especially during CMB and structure formation. So ultimately what it means is that I cannot use this, not only can I not use this temperature as a proxy to temperature fluctuation as a proxy to describe these neutrinos, I also cannot use the cold dark matter picture. Okay? And so in the end, what it means is that we're just forced to play with the entire full Boltzmann hierarchy, including all the momentum dependence. Okay, so that's actually what happens in codes like class or CAM today. When you work with massive neutrinos, it goes full on, full momentum, full Boltzmann hierarchy, solve the whole thing. Which is why if you ever try running class or CAM with massive neutrinos, it takes forever, because you don't have the luxury to make these assumptions. Okay? The same is also true, same reasoning is also true for warm dark matter. Okay? Warm dark matter is usually, like if you think about KeV, sterile neutrino warm dark matter, these are usually produced at a fairly high redshift, well, way before standard model neutrinos anyway, and when they're produced, they're actually relativistic as well. Except that warm dark matter is produced in the early universe at such an early time that they have had time to redshift. Okay, to a point that for the momentum of redshift to a point where they are, well, not cold, but not as hot as the standard model neutrinos. And typically, we're looking at KeV mass, warm dark matter. We expect the transition from relativistic to non-relativistic at maybe a redshift of 10 to the 6, 10 to the 7, depending on the exact mass. So they don't spend quite a lot of their time during CMB formation, and actually during CMB formation, they count as a cold as a matter, not as a radiation. But still, they still have a lot of residual free streaming effects left. So again, if you're interested to look at perturbations in warm dark matter, you have to take out your full Boltzmann hierarchy and solve the whole damn thing. Okay? Luckily, people have done it before, and they've come up with fitting functions, at least for thermal warm dark matter. And there's some approximations that you can use to simplify life a bit. But if you have a warm dark matter that is a little bit non-standard, maybe it has a funny distribution, non-thermally produced, and you have to go through the machinery and stick it back in and solve the full Boltzmann hierarchy, which can be quite time-consuming. But anyway, that's the non-interacting stuff of warm dark matter and neutrinos. Now, then let me also move on to talk about how we can model photons and baryons. Well, the idea of modeling photons, as you can probably guess, is similar to modeling massless neutrinos. Okay. And you can again define for photons, you can again define a temperature fluctuation, which in this case we call theta to distinguish it from the delta for neutrinos. And the left-hand side of the Boltzmann equation for photons would be essentially the same as the case for neutrinos, except that I just have to replace my deltas here with thetas. Now, what differs between massless neutrinos and photons is, of course, the fact that the photons can interact. They can scatter off electrons. In particular, you will have Compton scattering. Okay, so you have a free electron that might be floating around, and a photon can scatter off that, like so. Now, Compton scattering in general can change the energy of the photon, so you may wonder if using the temperature fluctuation as a proxy for the perturbed phase space density is a good idea. But as it turns out, the temperature region we're interested in is usually just around photon decoupling, okay? And that's at a temperature of around maybe 1 electron volt or so, okay? So what it means is that the typical energy of the photons that you are looking at that time will be much less than the rest mass of the electron, which is 500 keV. Okay. So instead, in other words, what it means is that I don't have to look at full-blown Compton scattering. I can look at the Thomson limit of the scattering process. Okay. So typical energy of the photons will be much less than the electron mass. So the Thomson limit applies. And when the Thomson limit applies, what it means is that the scattering does not change the energy of the photon, but it changes only its direction. Okay, so this means that it's okay to not track the full momentum distribution of these photons. I only need to check the direction of the momentum. Okay, so this again justifies why it is okay to just go straight to track the photons using only the temperature fluctuation as opposed to the full phase space density. Okay? So ultimately what it means is that my Boltzmann equation will look like this. I'll have d theta d eta, and then ni d theta minus d log q d eta, which is exactly the same as what we wrote down there for our neutrinos. But then I also have to tag on the right-hand side the collision integral. Okay. Now the way I've written it is, well, I factor out this. Theta. How do we define that? Theta I should define this here. Theta is f gamma df d log q, and then theta. Okay. So what I have on the right-hand side of the Boltzmann equation, it will be df bar photons, and then d log q, and then a collision term. Okay, I'm writing my collision term a little differently here. I'm writing it as df d eta collision, just to remind ourselves what this is. Okay? And this collision term here, as said before, changes direction of photons, of a photon, but not its energy. Okay? And that's a result of the fact that we're in the Thomson limit of quantum scattering. Now, Thomson scattering is really, really well studied. So we can already adopt a lot of what people have learned before from other fields and just use it. Okay? So, so if I'm looking at the rest frame of the electron, then the differential cross-section of differential Thomson cross-section looks something like this, okay? D sigma, the solid angle, is equal to the Thomson cross-section, 4 pi, and then you have basically a function, which I'll call omega, n hat prime, which basically tells you what happens if you have a incoming photon in the direction n hat, and what happens to it after the scattering. Okay, that's the direction of the outgoing photon n hat prime. Okay, we can rewrite it in many different ways, but this is just to just to tell you that it has a dependence on the the differential cross section depends on which way the photons are coming in and which way they are coming out. Okay, looks like this actually: 1 plus n dot n hat prime square. Okay, and this particular expression here is average over incoming and outgoing directions. Polarizations as well, sorry. Not average over directions, average over polarization. Okay. Now, of course, you can also keep track of the polarization of the photons. That's a whole different subject of CMB polarization. But at least as a first pass, you can just forget about what's happening with the polarization of the photons. Now, then, in order to figure out what is the collision term that needs to go into the right-hand side of the Boltzmann equation, and all I need to do is to just make use of the Thomson cross-section that we just wrote down, and then try to figure out what is the rate at which photons are being scattered out of a particular direction, and also the rate at which photons are being scattered into that particular direction from all other directions. Okay, so I can write down df d eta in the rest frame of the electron. Okay, this would be equal to minus a, the Thomson cross-section. It would depend on the number of scattering centers, so number of free electrons that are there in the universe. And I will have a dependence also on whatever is the phase space density of photons that are there in a particular direction n hat. And these are basically, this term here basically tells you about the photons that are being scattered out of the p n hat state. And then you're going to subtract away from that all those photons that are being scattered into the n hat state. Okay, so you sum over all solid angles, and then the phase space densities on the n hat prime states, and then also, of course, the angular dependence of the scattering. Okay, so that's how I construct a collision integral for photons being scattered in and scattered out of a particular momentum direction. Now, this is a fairly general expression. If I want to re-express it in terms of these temperature fluctuation parameters that I've defined, I can also do that. Okay, it will just look like this. I will have df bar photons, d log q, and then a sigma t ne, and this first term here will just become the temperature fluctuation in the n direction minus, sorry, that's a comma, 1 on 4 pi, and then a solid angle integration of the angular fluctuations, the temperature fluctuations in all the other angles, and then the angular dependence of the scattering. Okay? This is not completely the final answer. This is not what we stick back into this integral, because what I have here is what happens in the rest frame of the electron. But in general, of course, you know, the electrons are also moving around in the universe. So if I am to go from the rest frame of the electron back to the co-moving frame, okay, the frame that the observer, the co-moving observer is observing, then what I need to do is to also account for the fact that my electrons are moving. And so what you can expect immediately is that there should also be a dependence of the final collision term on the electron velocity. And indeed there is. It will look like this. Okay, so this is a collision term in the co-moving frame. I'll just have all of that bunch of stuff over there. Okay, which I'll call big cross x is, no, x is a bad thing. Let's call that y. You have all of that. And then there's also the velocity of the electrons that I need to worry about. In particular, it's actually the velocity of the electron relative to the Ni here is the direction of the incoming photon, okay? And then there's also this factor df bar d log q that you need to multiply because of the way we are writing our collision integral. Okay, yeah, so it's pretty horrible in general. But the bottom line is that now we have a collision term which is in the right frame. Okay, which consists of that bunch of stuff over there, plus an additional term that comes from the fact that my electrons are not at rest relative to the co-moving observer, so I have to account for that velocity as well. So now I have everything, and then I can just stick it back in here. And what I'll end up with is ultimately an equation that looks like this. Okay, plus Ni di theta minus d log q d eta is equal to what we call minus kappa dot, and then theta n hat minus 1/4 solid angle again, and then omega n hat prime plus ei ni. Right. Just two more things, because I really need to stop. The one thing is to define what this kappa is. Kappa dot, as you can see by just comparing what I have written up here and over there, is simply scale factor times the Thomson cross-section times the free electron density. So it's really just the rate, but we like to call it kappa dot because if I imagine integrating kappa dot over time, such that I get kappa instead as a function of time, then this thing here actually has a physical meaning that is commonly used in astrophysics. And This thing here is called the optical depth. Okay, so how far you can see back in the past. Okay, if you have way too much stuff in your way, you can't see, in other words. Okay, so that's the optical depth parameter that comes into my Boltzmann equation. And as usual, you can decompose your Boltzmann equation again into this huge Boltzmann hierarchy, and that's basically what you have once you do that decomposition. I guess I will be short dead if I don't stop here, so I will, and I will pick up from here, and then say a few words about the structure of this equation and what the physics that it implies relative to what we've seen before for cold dark matter and massless neutrinos. Okay, so I'm just going to stop here. Yeah.
Okay.
Yeah.
Any questions?
Yeah.
This order of the photons is going to track of the homogeneous in the electrons.
So I didn't hear you very well. The acoustics is not very good.
So for this order, in inhomogeneous for the photons, you don't need to keep track of the inhomogeneous in the electrons in the quantum standard.
You mean the number density? Yeah. So the number density that goes in here is actually just the background, because otherwise you'll be higher order. Yeah. Yes. There's one question over there. Maybe you need a microphone because the acoustics is very weird and.
Maybe a naive question, but is this how you calculate so all these equations you take into account calculate the temperature perturbations in the settled universe, or?
That's basically what's in the code that gives you the CMB.
Yeah.
And the large-scale power spectrum that people just download without knowing what's inside. Yeah.
Anybody else wants to